Hello everyone, this is Selda Kapan Ulusoy. I'm a faculty member at Erciyes University in Turkey. I work on reliability models, and today I'm going to present you a work, part of a project we did with one of my graduate students, and its title is Aircraft Propeller Reliability Analysis. Let's look at the problem definition. We would like to conduct a reliability analysis for the propellers of an aircraft fleet. There are 34 aircrafts in the fleet. They are all from same manufacturer and in same age and work under the same operating conditions. 72 propellers serve the fleet. When a propeller breaks down, a working propeller is installed to the aircraft to keep it running, and the broken propeller is sent to the repair, and after repair it is put into storage for the future use. In this company, maintenance crew is composed of 1 engineer and 2 technicians. Main steps of the analysis: first, collecting and organizing the maintenance data. Second, determining the most suitable content process model representing the failure behavior of the propellers. Third, estimating the model parameters. Fourth, checking the model's goodness of fit. Fifth, estimating reliability measures for propellers. So let's look at the details of the first step. In this company, maintenance records were kept in different files at different departments. So we had spent some time to merge all the data into one file. And some of the records had missing parts. So we had several meetings with the maintenance crew to get information on the missing parts and also discuss the accuracy of some of the data. Example of the data we used in analysis is you can see in the table. A propeller is tracked by its serial number, and the failure times kept in flight hours. For example, here propeller P01 had its first failure at the 1909.7 flight hours, and the second failure 2422 and 22.2 flight hours, etc. We can summarize the data as the number of propellers that have suffered a given number of failures, and you can see that failure numbers are changing from 0 to 5, and 22 of the propellers had no failures at all. We had to do some operations on the data. All propellers are from the same manufacturer. They are in same age and their working conditions are same. So we assume that they are homogeneous. Also, we discussed this with the maintenance crew. We know that they're homogeneous, and therefore maintenance data of 72 propellers are pooled for modeling purposes. In the second step, we have to determine the most suitable model, counting process model. Counting process model is a kind of a stochastic processes. And because of the time limitation, I don't give the details of the models and the tests that we used, but for your convenience, I added their references. For a counting process, there are 3 main random variables. These are NT, number of failures occurring by time t, SE, occurrence time of the ith failure, and TI, the time between failure I minus 1 and failure I. And you can see these random variables below in the NT versus T graph. That NT is the number of failures on the y-axis, and the time is on the x-axis. Here, S1 is the first failure time, S2 is the second failure time, etc. And I gave you the example from our data here. So basically, there are four main types of counting process model. These are homogeneous pass-on process, renewal process, non-homogeneous pass-on process, and imperfect repair processes. All models here have different assumptions. Here, renewal processes and non-homogeneous processes, non-homogeneous pass-on processes are a special, let's say, generalization of the homogeneous pass-on processes. So to decide which model is best, we have to apply trend tests to the data and then decide which model is the best one. In our modeling effort, we start first with the non-parametric MCF model. Non-parametric and MCF estimates the mean number of failures per system as a function of time using only data. So we don't assume any parametric model here. So data can speak for itself. Shape of the MCF gives information on the failure behavior of the system. If shape is convex, system fails more often in time, so it is deteriorating. And of course, time between failures have a decreasing trend. If shape is concave, system fails less often in time, so it is improving, and TBFs have an increasing trend. If shape is linear, then intensity of the failure is constant in time, so the system is non-committal, TBFs are identically distributed. So let's look at the MCF of the propellers. In the graph, you see it has a, approximately convex shape. So we can conclude that propellers are deteriorating. This is expected since a propeller is a mechanical unit and the mechanical units wear out in time. So next we applied the trend tests to see that we can conclude, we can support this conclusion. So we used two trend tests, TT-based Milter handbook and TT-based Laplace test. When the systems are homogeneous, TT-based tests are more powerful on recognizing the trend than the combined version of these tests. If the systems are heterogeneous, you have to use the combined version of these two tests. Let's look at the hypotheses. Null hypothesis is all processes are HPPs with identical intensities. This part here about the homogeneity of the units. And the alternative hypothesis is an HPP with monotonic intensity function. Now, let's look at our test results. As you can see from the table, p-values are 0 for the tests, so indicating that the NHPP is the appropriate model for the failure behavior, so we rejected H0. But here you should be careful when you are using TT-based tests, because when you reject H0, it could be that the systems actually have a HPP model, but their intensities are different. So if you are sure that systems are homogeneous, then you should use the TT-based tests. Okay. So we decided HPP is the suitable model, and now I will give you very little summary information. An HPP model is also called minimal repair model. After the minimal repair, the state of the system is almost the same as just before the failure, as bad as old. It is called as bad as old. So this is the basically the definition of the minimal repair. In real life, this can be justified since when a system fails, only a small number of parts are changed or fixed in the system. In an NHPP model, time between failures, TBFs, are neither independent nor identically distributed because they have a trend. An HPP model is characterized by its intensity function, which is denoted by little wt, and wt's measure is failures per unit time. So the cumulative rate of the process is denoted by capital letter WT, and we can get this little w to the intensity function, integrating it from 0 to t. So in an HPP model, the number of failures in an interval 0 to t is Poisson, has a Poisson distribution. So you see here that from Poisson distribution, you can write the in an interval the probability of n failures occurring. So again, the expected value of the number of failures in an interval is here, expected value of nt. It is denoted by WT. So cumulative failure failure intensity is equals to expected number of failures. Of course, in Poisson distribution, expected value and the variance are same. So variance of the number of failures are again equals to cumulative intensity function, the value. So a special form of intensity function is called a power law model. And the power law model generally provides good fit to the maintenance data, and it is used in practice and also in academic work. So we fit the power law model to Propeller data. Now let's look at the power law model again very briefly. The intensity function is, as you see here, lambda beta t to the beta minus 1. Here, lambda and beta are parameters of this model. Lambda is called scale, and beta is called as shape parameter. Beta parameter is important because its value tells us about the failure behavior of the system. So if beta is between 0 and 1, then intensity function is decreasing. So the system is improving, and times between failures has increasing trend. If beta is greater than 1, intensity function is increasing, so the system is deteriorating, and the times between failures has decreasing trend. If beta equals to 1, then the intensity function is constant in time, so the system is non-commutal, and power law model reduces the HPP model. As before, I said that it was a generalization, and HPP is a generalization of an HPP. So now let's see model parameters. In the third step, we have to estimate the model parameters. Our data is time truncated. So using the power law model likelihood function for the time truncated data, we found the maximum likelihood estimations of lambda and beta, and it is given in the table here. You see the estimates, the standard error of the estimates, and the 95% confidence intervals for the for asymptotic confidence intervals. These are. So here we have to look at the value of the beta. Beta is approximately 1.4, and which is greater than 1. So we can again here conclude that propellers are deteriorating. So this supports the non-parametric MCF result and the trend test results. So in the fourth step, we have to check the adequacy of the model, our model. First, we did look at the MCF graph estimated from the model and the non-parametric estimates. So here you see the graph. On the graph, blue points are empirical estimates of the MCF, mean cumulative function, which is, as I said, it gives you the mean number of failures per system as a function of time. So it is calculated, it is calculated by Nelson-Island method. And here the red curve is the estimate of the MCF from our model. So as you see, points closely follow the curve. So that from here we can say that power law model provides a good fit. Now we will check, actually we will use the formal goodness of fit test now. How are we going to do this? Here, if you look at the equations, below equations, we can fit, you can see that we can fit a linear regression model to ln NT versus ln T, because here you see expected value of NT equals to lambda T to the beta. So if we take the natural log of values, so we can get this below equation, which is linear. So this is called, after finding the regression here line, we can look at the fit, and this is called the ln T versus ln T, ln NT versus ln T graph as a Duane plot. So for here, then we can check the coefficient determination coefficient R square for the model. And, if R square is high, then we can conclude that model provides a good fit. But somehow how should R square, how big should be R square? It is somehow subjective. So in this work here, in the reference 6, they, through the simulation studies, the authors provide the critical values to test according to R square. So for this test, the null hypothesis is the underlying process is PLP, power law process, and the alternative is the underlying process is not a PLP model. If the model R square from the linear regression model R square is less than the critical value, then we reject the H0 at the significance level of delta. And again, in the paper, they provide the critical values table. So we estimated the regression line. We fitted the regression line basically, and as you see from here that we have a good fit with the data, and the equation is here. For this regression line, R square is equals to 0.982, so which is quite a high. But as I said, we will check this with the critical value. If we look at the table on the 0.05 significance level, the critical value is 0.93. So since the model R square is greater than the critical value, we cannot reject the null hypothesis, so that we can say that PLP model provides a good fit to the data. On the fifth step, we have to estimate the reliability measures for the propellers. So first measure is the mean number of failures in an interval of AB. So we can find the expected value of NT through the integrating intensity function over the region AB. So we can find this way the first reliability measure. Second reliability measure is actually the reliability of the system over an interval AB. So how are we going to find this? Here we have to notice that the reliability is the probability of failure-free operation during the interval AB. So we can write reliability AB as the zero number of failures occurring in the interval AB. So we can write this, we can find this probability using the Poisson distribution. Here below table, you see that for several intervals from 0 to 1,000 flight hour, 1,000 to 2,000 flight hour, etc. We calculated the mean number of failures and the reliability values for that intervals. So again, as we expected, because we know that this system is deteriorating, even though time intervals, as you see, same, they have all same length, the number of failures occurring inside that interval, the mean number of failures are increasing, and of course reliability is decreasing. So the third reliability measure is the instantaneous mean time between failures, which is denoted by IMTBF. This is the mean time between failures at time t. So we should be careful about that. And IMTBF is found by 1 over the intensity rate. And the fourth measure is the cumulative mean time between failures. This is the cumulative mean time between failures is a function of WT. So it is over the interval 0 to t. And CMTBF, you can find the CMTBF as T over expected value of NT, and if you do some calculations, you'll see that it's equals to beta over the intensity function. Again, here in the table for some time points, we give IMTBF and CMTBF. Here, CMTBF, you should keep in mind that CMTBF here, for example, let's say on the third row, it is the cumulative mean time between failures over the interval 0 to 3,000 again. Again, of course, again, as expected, we see that these values, both values are decreasing. So, for example, let's look at when a propeller fly 6,000 hours. At the 6,000 flight hour, we expect the IMTBF as 389.4 flight hours. So looking at all these reliability measures, it says that preventive maintenance plan of the propeller needs to be revised as they are aging, so that the company can keep the safety standards according to its benchmarks. Our presentation is over here, and you see the references. You can get more information from the references. And if you have any question, you can write me from my email, and see you all in other conferences.